Robots are continually evolving, and most of the newer type of robots are interacting with people. As such, there has been an enormous demand in the industry to enhance the safety of personnel working with these collaborative robots. The objective of safety is to prevent the occurrence of an injury, harm, or danger. Safety is essential, all the way from the enterprise to the operator level. The absence of safety can cause damage, death, financial loss, reputation, and productivity. However, with proper planning, training, and execution, safety can be practiced and maintained at all times. As you'll see throughout the course, it takes a proactive safety approach. We build upon a three-tier safety pyramid, which lays safety fundamentals, meters safety performance, and continually provides the opportunities for improvement. The safety pyramid has the 3E tools. The most effective, elimination, refers to physically removing a hazard. Engineering controls, which incorporate programming, safety cutrins, etc. to prevent danger. The third tier is enterprise controls, which changes the way an operator works through work instructions, restrictions, etc. Several continually emerging robot safety standards provide the framework to enhance safety. ISO 10-2018-1, 2011, Part 1 talks about the safety essential for industrial robots. It addresses robot manufacturers. The standard evolved from the 2006 edition and includes the concept of risk assessment at the application level. ISO 10-2018-1, 2011, Part 2 incorporates the safety requirements at the integrator level. The ISO TS 15066-2016 builds upon the two mentioned standards and provides safety requirements for collaborative industrial robots. Although this technical standard primarily targets collaborative industrial robots, there is a cross-transfer of knowledge applicable to traditional industrial robots. The Robotics Industries Association, RIA, put together a technical report in 2016, the RIA-TR R15.606-2016. The report enhances the safety of personnel with collaborative industrial robot systems and represents the primary focus of the course. Although a technical report, it's continually improving and is expected to mature into a standard by early 2020. Moving on to control reliability of the robots. Control reliability is a concept and represents a function of relative safety. However, the reliability is difficult to quantify. A matrix provides a method to validate a robot or robotic system design. The performance level varies from B to E and structure categories from 1 to 4. Both represent from negligible to high risks, which we will get into more detail later. The robots are expected to meet the safety requirements of performance level D with the structure of category 3. Based on the input of a risk assessment, it may require higher control reliability based on the probability of occurrence of a hazard. At this point, it will be helpful to understand what distinguishes a collaborative robot from a non-collaborative robot. Traditionally, an industrial robot would exclude operator access to the operations area while the robot is still active. A robot is usually protected with a fence around it to prevent human interference. Now, in an instance where an operator does enter the cell without hitting stop button or absence of present detector, the robot can cause harm to the operator since this does not come to a protective stop. On the other hand, Collaborative robots have inherent safety features that can detect a threshold contact force and can instantly stop. In these collaborative workspaces, robots exhibit precision and power, and humans can solve imprecise problems. Such a collaborative application finally affords robots and humans to share the same workspace. We introduced the critical difference between a collaborative and non-collaborative operation. Let's dig deeper into different kinds of operation based on a function of time and distance between the operator and a robot. This foundation of different kinds of operations will be beneficial as we progress through different facets of the course. This understanding will help you recognize and design the type of operations that you would like to incorporate in your application. The three types of robot operations are coexistence, cooperation, and collaboration. In a coexistence type of operation, a robot and an operator function at different times and in separate workspaces. A protective fence surrounds the robot and access doors are locked. This fence prevents human access while the robot operation is active. However, an operator may stop the robot operation and enter for required maintenance in industrial robots. In a cooperative type of operation, an operator and a robot work in the same workspace. However, the different stages of the tasks are realized at various times during the operations. These operations require adequate safety measures in place. For example, progressive padding, pressure mats, etc. These measures prevent operator access to the restricted area of robot operations, as it may cause potential harm or an injury. Loading and unloading of parts is an example of a cooperative operation. Now on to a final type of operation, the collaborative operation. In this type, an operator and a robot perform tasks within the same workspace. Unlike cooperative, a collaborative operation is realized at the same work time. The collaborative activity is an evolution in the world of robotics and represents a primary focus for the course. Since an operator and a robot work in such proximity, the three factors, that is, force, speed, and path of the robot must be controlled or restricted. Now that we've established our fundamentals, let's take a look at the robot industry evolution. We'll also transfer knowledge from industrial robots to collaborative robots.